Please join me in welcoming Dr. Kerry Emanuel.
Thank you so much. That's great. Well, thank you very much, Madam Chancellor, for that very generous introduction. That Time magazine thing, another person on that roll of 100 that year was Osama bin Laden, so I'm not so sure I was too delighted about that. But, when we planned this talk many months ago, that was before this sort of catastrophic hurricane season we've just had, and so I have to admit to you that there's a little bit of heaviness in my heart in talking about hurricanes now, but it's still very important, and for me, a very fascinating subject. And I want, before I get into my formal talk, to say to you that the reason that I am in climate science, and most of my colleagues are in it, I've been in it for decades, is for the same reason that almost any scientist you care to meet is doing science, is we love to do it. We're really driven by curiosity about the natural world. That's why we're in it. And with all the politicization of climate science, it's extremely easy to lose sight of what a fascinating field it is. I would be talking to young people, trying to get them to go into climate science if we had absolutely no global warming problem at all, just because understanding how the climate system works and why it's varied the way it has in the past is such a fascinating problem. And I'm always trying to get to rekindle people's interest in it and look at it as a fascinating scientific problem and not as a primarily political problem, although it has become that a bit. But I want to focus tonight on the science and try to give you a sense of the excitement about the science of hurricanes and hurricanes as a natural phenomenon. So the general program for tonight is to, first of all, talk about the human side of this, the global hazard. What do the statistics show us about the seriousness of this problem? To talk about inferences from both historical records of hurricanes, and more recently we've figured out how to see hurricanes to some extent in the geological record, which is a fascinating, quite new field. Then to get into some of the basic physics of hurricanes, which are in themselves quite interesting. And then something quite new is how can we use our understanding of hurricane physics to do a better job estimating risk, so that, for example, people's insurance premiums can be a bit more rational than they are today. How do we do a better job estimating risk? And I'm going to wind up the evening talking specifically about North Carolina's hurricane risk. I'm going to be talking about some of the past storms in North Carolina's history and what we think might be happening in the future. So that's where we're headed tonight. There are, alas, on average, about 10,000 deaths per year globally since 1971 from tropical cyclones, which is the generic phrase for what we locally call hurricanes. So they are very serious. $700 billion, 2015 US dollars, in damages globally since that time. It's a lot of money. And this is the really distressing thing, and it's a demographic problem. A global population exposed to hurricane hazards has tripled since 1970, tripled, okay? So people are migrating in droves to the coast, not just here in the US, but in many parts of the world. And so they're driving up deaths and damages from hurricanes, and that would be true whether the climate changed or not. And that's a big problem. I won't be addressing it tonight, but it's partially a problem of our own making. So what are the risks of hurricanes? Well, everybody thinks of a hurricane primarily as a windstorm, and the Weather Channel will send out intrepid reporters to stand in hurricane winds or try to stand up in the winds, and it's very dramatic. That's what we think of them as, and they are. But there are also terrific rainstorms, as you saw recently in the case of Hurricane Harvey in Texas. And statistically, the most lethal part of a hurricane is the storm surge. And the storm surge is physically the same thing as a tsunami, and some of you have seen the really horrifying videos of tsunamis in Japan and Indonesia not so long ago. And it is the same thing, except it's excited by wind rather than by shaking seafloor. And I feel it's so important that people who who live or contemplate living near the beach understand what a storm surge is. It's a tsunami that arrives in the middle of a hurricane. I'm going to show you, if I can get it to work, a film of this. This is taken from an amateur photographer in the Philippines. Okay? That's a storm surge. You cannot outrun that. You can't survive that. And in fact, the man who took this movie was very lucky to escape with his own life. Okay? I don't know how well you could see that, but that's what you're up against in a big storm surge. And if you ever are in the way of a hurricane, I want you to remember that film. If the authorities tell you to get out, that's primarily what they're worried about, and you should be worried about that. And in fact, it is the water, not the wind, that all around the world is the big killer in hurricanes, and that includes the United States. So if you look at the period 1970 to 1999, what you see at the top is that most of the deaths from hurricanes are from drowning, either in fresh water from torrential rains, or the second bar down is from salt water, that's the storm surge. In the rest of the world, those two numbers are reversed. It's mostly the storm surge. Wind is pretty far down the list, and then there are a few odd things that go along with hurricanes that also cause mortality. But fresh water and salt water are the big problems. Now, curiously enough, in the United States, water damage from storms is publicly insured. It's insured under the federal flood insurance program. And whereas wind is privately insured. Now, there's enough, in fact, most of the insurance industry worldwide, most of their payouts for natural damage, natural disasters, is for hurricanes. And they've poured money into understanding this risk, which is great, okay? But because there's no money to be made in freshwater and saltwater floods, there's been comparatively little spent on that. And yet that's the big, and you have one of the world's experts on storm surge and Rick Lutic here. So if you ever are interested, that's the person to go to talk to. That's the person I go to talk to about that. Now, let's get to the whole problem of how do we tell whether there's any sort of systematic change in hurricane activity. There are lots of reasons to want to know this. It's not just a question of global warming. We'd like to know, are there more hurricanes during El Nino years or fewer? We'd like to know how they're related to natural climate phenomena. And if we want to do that empirically, we have to know how hurricanes have varied in the past. But this is very problematic. So before 1943, all we really have to go on is what I call anecdotal history. It's ship's logs, written histories from coastal cities, newspapers, that sort of thing, not much by way of actual measurements. In 1943, we introduced reconnaissance of hurricanes by airplanes. And it's a great thing to do. I've done it many times. I think when I retire, I'm going to start a hurricane safari and take paying customers in to see the eye of a hurricane. It's a fantastic experience. But more importantly, it's actually allowed us to make measurements and much better records of these storms. Not until 1958 was there a technical development that allowed us to actually estimate wind speeds from research aircraft. Believe it or not, before that, we really couldn't do that quantitatively. Then by 1970, we had enough Earth orbiting satellites that we're fairly confident we've detected just about every hurricane that's occurred on the planet since then, but not necessarily measured them well. Seeing them from space is one thing, knowing how strong they are or other characteristics is quite another thing. Then there was a nice development in 1978, satellite scatterometry, which allowed us to detect some aspects of the wind field from space. Unfortunately, aircraft reconnaissance stopped in the Western Pacific in 1987, and the only place that does that systematically today is the Atlantic, and which is only 12% of the global hurricane activity. Just this year, we got a brand new instrument in space called Cygnus that promises to do a much better job measuring surface winds and hurricanes. Now let's look at the Atlantic hurricane record. This is a graph designed to show you what the problem is. So if you go into the official hurricane database and you just count the number of major hurricanes per year, going all the way back to 1851, that's the red curve. And that little red dashed line you see there shows you the trend line for that. And you might look at that and say, oh my God, there's been a steady or maybe not so steady upward increase in the number of big storms. Okay. Now the blue curve is just the subset of those storms that made landfall or traveled over land, either passing by the Lesser Antilles, which were very populated over this whole period, or making landfall in the continental US, or both. And they also show an upward trend, but it's a lot less, right? And we don't really think that the trend of open ocean hurricanes, which is really the red curve, was a lot greater than the trend in landfalling hurricanes. What we think is true is we missed a lot of open ocean storms early in this record. We just didn't see them. They didn't hit a ship, they didn't hit land. Today, we do see them with satellite and aircraft. So yeah, there's an evidence for an upward trend, but we're up against big problems with the early part of the record. One thing we're more confident in, because we're using satellites to detect the trend, is shown in this graph. This is a graph that goes from 1980 to 2015, and it shows from satellite measurements only the latitude at which hurricanes are observed to reach their peak intensity. Okay, and the upper graph is for the northern hemisphere, and the lower graph is for the southern hemisphere. In both hemispheres, hurricanes are peaking further and further away from the equator and closer to the poles. And that's a trend that we predicted some decades ago, and it's there. It's very robust in the satellite measurements. So that's one trend that we are able to detect with satellites that make use of their best abilities. I mentioned to you that we have this new satellite, and you're among the first people to ever see this plot. Maybe a little hard for you to see, but they are swaths of satellite measurements through Hurricane Harvey when it was in the western Gulf of Mexico, and the colors correspond to wind speed. And these are very early results, and I got them from my colleague Chris Ruff at the University of Michigan, and they haven't been calibrated yet. I couldn't resist showing them to you, because they promise, these can see through rain and other things. They promise that we're going to globally do a better job measuring surface winds as we go forward, thanks to technology. All right, so the historical records have these problems. Well, how are we going to deal with that? One way to deal with that is by looking at the geological record. And there's a new field called paleotempestology, which attempts to do this. And basically what happens is if you go to many parts of the East Coast or the Gulf Coast, including North Carolina, maybe especially there, you'll see a profile around the beach that looks like this. So the ocean is on the left. You're looking up, looking at a cross-section that's vertical. Typically, you have a beach, like the barrier islands, and then inshore of the barrier islands, you have either a brackish or freshwater lagoon or a barrier marsh, it's called, a marsh just behind the sand, sometimes both. And in these places, you have plenty of plants growing and dying and settling to the bottom and creating mud. But once in a while, a storm will come, and the storm surge will wash sand into the marsh or the lake, and then it goes back to the usual plants growing and dying. And so if you take a core, and what my colleagues who do this do is they fill a rubber dinghy full of graduate students with coring devices, and they go out. It's a very low budget experiment, but very effective. They go out into these lakes and lagoons, and they take cores. You see in the core mud interspersed with sand layers. And you can radiocarbon date the mud and discover when those sand layers were put down. So you can see historical hurricanes, but you can also see prehistorical hurricanes. And in the best example, by my colleague Jeff Donnelly at Woods Hole, there's a core that goes back almost 7,000 years. So what you're seeing, if you focus on the upper panel there, and you read it from left to right, it goes from 6,000 years ago at the left to today on the right. And the upper graph shows a measure of the coarseness of the material in the core. So it's a measure of how much sand there is. So each of those upward spikes corresponds, we're pretty sure, to a hurricane hitting this place. This is from Vieques, an island just to the east of Puerto Rico that really got hammered, by the way, in Hurricane Maria. So there's another sand layer for a future geologist to go after, but This core was taken well before that. And you can see that there's a pattern there. There are periods of almost a millennia with not much, and then there are periods that were very active. The middle graph it shows something completely different. It's a geological proxy for El Nino events, and every one of those upward spikes corresponds to an El Nino, and you can see there that likewise there are periods where there are lots of El Ninos and periods of hundreds of years long that there aren't many. And you can see that when there are lots of El Ninos, there aren't many hurricanes, and vice versa. So this kind of geological detective work is giving us for this first time a real insight into how empirically hurricanes are related to a particular climate signal, in this case El Nino events. And it's well known today that an El Nino year will be relatively quiet in the Atlantic. Now, we don't have just observations, okay? You're probably with me kind of so far tonight. It's not so difficult to present observations to you. It's a little bit harder to tell you the thing that actually gives us confidence that we begin to understand them. That's theory. So I'm going to take a few minutes of your time to talk about the theory of hurricanes. A hurricane, this is a vertical cross-section. It's more of a cartoon of a hurricane. So you go at the center of the storm is at the left, and you go up, this is in kilometers, about 16 kilometers or roughly 10 miles, and you go out 200 kilometers, about 120 miles or so. And a hurricane is a giant engine that converts heat energy into the energy of the wind. So we call that a heat engine. Most engines that we're familiar with, like the engine in your car, converts, unless you're driving an electric car, converts heat energy into mechanical energy. And long ago, in the middle of the 19th century, French scientists understood some of the very basic facets of heat energy, that you could only convert a certain fraction of that into work or mechanical energy. That fraction turns out to depend on how great the temperature difference is between where you put the heat into the engine, like the cylinder inside your piston engine of your car, and where you take it out, like the radiator. So that same very gifted polymath, Sadi Carnot, said there's a particular kind of engine which is most efficient at converting heat into mechanical energy. And that engine, ideal engine, bears his name. It's Carnot. And if any of you ever took a course of thermodynamics, you will have heard of a Carnot engine. But you won't probably see an example of one because they're so ideal that nobody ever thought one actually existed. But a hurricane turns out to be an almost perfect ideal Carnot engine, the most diabolically efficient engine in nature for converting heat into wind. Now, how does it do that? So the heat comes into the engine through the ocean. And the way it does that is the evaporation of seawater. So you know that when you get out of the shower or out of a lake or something, even if it's a warm day, you feel cold because water is evaporating from your skin. And it's taking energy out of your body. And the energy doesn't disappear, it gets added to the air. And that's precisely what's happening. In the strong winds of a hurricane, you get enormous evaporation of seawater, and that's the driver. Now, if you were to be so unwise as to go for a hot air balloon ride in a hurricane, you start at A, you would find yourself sucked into the vortex, you would spiral into the center. And when you got to the eye wall, assuming you survived that long, you go rocketing up this eye wall cloud that you see at the left there, and out and back down. And the lurid colors there are a measure of the heat content of the air, and you notice that from A to B it increases a lot. That's reflecting all this evaporation. From B to C it doesn't change, it's conserved. We call that an adiabatic expansion. And from C to D you lose the heat you gain from the C, and that's by infrared radiation to space. And then from D to A it's conserved again. And that turns out to be the four legs of a Carnot heat engine. So we can use that actually to calculate a wind speed. And my mother told me never to show an equation after dinner. And I'm only going to briefly violate that rule and tell you that there is such an equation. It's the E equals mc squared of the hurricane world. It tells us what v squared is, the square of the maximum wind speed you can theoretically have in a hurricane in a given environment. You don't have to, I'm not going to go through this with you, you just have to know it exists. And we can use it to make maps like this of the peak wind speed you could have in a given climate. So this is for the climate of the late 20th century, and it's from observations, and it shows you this calculation of a theoretical maximum wind speed you can have over the course of a year at every point over the oceans. And it's in meters per second. If you want miles per hour, roughly multiply that by a factor of 2. It's a little bit more than 2, but there you go. And you can see that you can have hurricanes precisely in the places you observe them, the equatorial oceans, the tropical oceans, here in the Atlantic, everything from the tropical Atlantic through the Caribbean and the Gulf of Mexico. That's where hurricanes develop. And that gives us some leg up. Now, we also know from very simple theoretical calculations that if you add a greenhouse gas of any kind to the atmosphere, like carbon dioxide, this potential goes up. And this shows how this potential intensity, this maximum wind speed, increases with the number of times you double CO2. And so if you double it once, it goes from about 67.5 meters per second in this particular climate to something like 70.4 and so forth. So it goes up, but it doesn't go up indefinitely. It actually saturates when you get to very high CO2 content, and it doesn't go up beyond that. That's the good news. I hope we don't ever climb that far on the graph, but it saturates at a certain level. So in 1987, I actually 30 years ago, wrote a paper predicting that it would go up because CO2 is going up, and guess what? It's going up. So this is a map showing from observations the trend from 1980 to 2010, the actual rate of change of this potential intensity. This is not from hurricane observations, it's just from climate data. And the graph didn't come out too well on the screen here, but where you see red, it's going up. Where you see blue, there are a few places where it's going down, although those tend to be places where you don't see hurricanes, where it's already very small. So yes, the potential intensity is going up. And if we look at climate models, like this particular one, this is a projection for the trend over the next century. If we do nothing to curb emissions, so assuming that carbon dioxide content just keeps going up, we see a trend of a few meters per second, say 5 miles per hour per decade. Now that doesn't sound like a lot, but over 5 or 6 decades it is a lot. And when you consider that the destructive power wind actually goes up very fast with wind speed, like the cube of the wind speed, that translates, unfortunately, into a lot of increase in destructive potential for hurricanes. So let me just summarize a little. This is all I'm going to do by way of boring you with theory tonight, but except for the few who aren't bored by theory. Potential intensity increases with global warming. And we think as a consequence that the incidence of high category hurricanes, the rare 3s, 4s, and 5s, like Harvey and like Irma and like Maria, will probably go up. And we made this prediction 30 years ago. Because of the shape of the curve I just showed you, we think it should go up faster, not in the deep tropics, but in the margins of the hurricane zone, in the subtropics, which is probably why the satellites are showing us this northward or poleward migration of the latitude at which hurricanes reach their peak. And this is very, very elementary physics. Hurricanes should rain a lot more as the climate warms. You all know that warm air is wetter than cold air, and it's not much more complicated than that. The air going up into hurricanes is wetter if it's warmer, so it rains more. Okay. Can we do better than that? So I've sort of said that, well, the thermodynamic potential is going up, hurricanes should rain more, but what does it mean for North Carolina? I mean, global warming isn't uniform. The tracks of hurricanes could change. You could have stronger hurricanes that stay offshore, where nobody really cares about them. How do we make more definitive predictions or projections about that? So one thing we could do is to try to turn to a global climate model to do this. But this is tough, and it's because global climate models don't have enough computational power to really simulate hurricanes. And what I'm showing you here is a graph taken from a really good global climate model that shows the number of hurricanes at each wind speed that you see on the x-axis. So there's a peak of very weak hurricanes. Most hurricanes that form on the planet are very weak. You see that red line reaching a peak. And then as you go to higher and higher intensity, there are fewer and fewer storms. The black line is what we observe. The vertical black line is the division between Category 2 and Category 3, and 80% of the destruction is done by Category 3 and higher hurricanes, even though they're rare. And what you can see by looking at the red line is that global climate models don't simulate destructive hurricanes. They can't. They don't have the power to do that. They can only simulate the weak ones. There are basically no simulated storms, the red curve to the right of that black line, whereas nature, unfortunately, does produce those powerful storms. So we really can't ask global climate models to really, in a quantitative way, deal with risks. So how do we deal with that? What we do at MIT is we take a really good hurricane model that we developed for and is used for actual weather forecasting of real hurricanes in real time. Greg's probably seen some of our forecasts. I'll have to ask you offline what you think of them, but we do make them. We take that same model and we do this. We take the global climate state that is simulated by a suite of global climate analyses or climate models, and we take that large-scale state and we, conceptually scatter proto-hurricane seeds all over the planet. And the next step is to see where they're going to travel, and that turns out to be a fairly simple problem. They move with the large-scale winds, which the climate reanalysis or climate model is perfectly capable of simulating. The hard step is to calculate their intensity, and we use this very specialized hurricane model that's coupled to the ocean, which is very important to do that. And this model predicts that the vast majority of these seeds you put down fail. They just die. That's actually what we want. Only the seeds that you put down in an environment favorable for the development of hurricanes actually develop. And so it's kind of a natural selection technique where we put down all these seeds and it's only the ones that are fit or in a fit environment that survive. And we use those survivors to sort of estimate the climatology of hurricanes, and we can easily create 100,000 survivors, so we can get very robust statistics. But the proof is in the pudding. Does it work? If you run it against the present climate, does it work? Well, I wouldn't be here talking to you if it didn't work. I wouldn't be wasting your time. It does seem to work. So this is an example of a mere 1,000 events simulated globally by this technique in today's climate, or the climate of a few decades ago. These are the hurricane tracks. Those of you who've seen charts of hurricane tracks will have a mental model you can compare that to, but it's basically okay. The colors indicate the wind speed in the hurricanes along those tracks. What's really nice is if we look at the number of events whose lifetime peak wind speed exceeds the value now in the quaint unit of knots or nautical miles per hour on this axis. So the blue is from historical hurricanes. So there were roughly 12 per year in the Atlantic whose lifetime maximum wind speed exceeds 40 knots, and a much smaller number that exceeds, say, 140 knots. And the red bars are from the technique I just briefly described to you. So we run, and it looks pretty good. I mean, you get a pretty good comparison between those. So we run this through the mill and subject it to a lot of tests. Remarkably, it actually does a not too bad job hindcasting, if you will, the interannual variability of Atlantic hurricanes. So this is a chart that goes from 1980 to 2012 or something like that, showing a quantity called power dissipation. It's a measure of how powerful hurricanes are summed over a whole year. The blue is from actual hurricane data. The red is from this technique. So we capture a lot of the interannual, much more than we thought we would, interannual variation. We can now run this on a unique NOAA global reanalysis of climate. This is going back in time, all the way back to the middle of the 19th century. And when we do that, we don't have good historical records of hurricanes back there, but this is what this technique sort of predicts would have happened in the past, given the large-scale climate state that we measured in the past, going from 1851 or something, more or less to the present. The red is the year-by-year number of major hurricanes by this technique. The green is just a smooth rendition of that. And so you see some very intriguing ups and downs, including the famous North Atlantic hurricane drought of the 70s and 80s, which everybody knows about. There were very few hurricanes during that period in the Atlantic, during a time when there was tremendous development of the US eastern and Gulf coasts. And that lull is a very interesting thing, and a lot of us believe that it was a man-made hurricane drought. What I'm showing you here, turned upside down in blue, is something we actually have a very good handle on, which is the emissions of sulfur from European power plants. Now, why would I put that curve on this graph? Well, it turns out European sulfur gets swept down in the summertime circulation over the Mediterranean, then over the Sahara Desert, and out to sea over the tropical Atlantic and the Caribbean. And it is very bright. It forms sulfate aerosol particles that reflect sunlight and cool the oceans, and we think, and models tell us, reduce hurricanes. So we put that sulfate emissions reached their peaks in the 1970s. And that's where the blue curve reaches its dip there. I've turned the blue curve upside down. And then we had the Clean Air Act, or acts, both here and in Europe, and the sulfate emissions went down again, and the hurricanes came back. And we don't think that's a coincidence, which is not to say, please don't tell anybody I'm telling you that we shouldn't have passed the Clean Air Act, but it was a silver cloud with a black lining, and I'm showing you the black lining here that we brought back the hurricanes. So this is the kind of thing we are beginning to learn from these kinds of exercises. Now, once we have these hurricanes, we can use them to drive hydrodynamic models of storm surges. And I'm showing you a grid that we used to do this for a study we did for the city of New York in 2010. This is before Sandy, trying to predict peak surges at the southern tip of Manhattan Island. And there's two grids on here. One is from a public model called SLOSH, which is okay, and then a really great model, which is the irregular array of red dots called ADCIRC, of which Rick Lutic here was a principal developer of that model. It's the state-of-the-art model that we all use when we want to try to get the right answer for this sort of thing. So we used those two models, and we came up with this estimate of the risk of storm surges at the Battery in Manhattan. So the way to read this is the surge level from a hurricane is in meters at the Battery is in meters. That's on the y or vertical axis. The return period is just that. So sorry about the exponents there, but 5 times 10 to the 2, it's 500 years. That means that there's a 1 in 500 chance of a surge of that particular level in any given year. And if we then, this was before Sandy, if we put Sandy on there, we would estimate that Sandy surge was, at least in the climate of the late 20th century, would have been about a 1 in 600 year event. In other words, Sandy was a very, very rare surge event. And one of the things we'd like to know going forward, is it going to continue to be rare or not? But this, and other groups, by the way, have also given similar estimates for that. That was a very, very unusual event. Now I'd like to talk about this year's hurricanes, beginning with Harvey, and try to use the same method to answer a kind of question that we think we can answer. We cannot answer questions like, was Harvey caused by climate change? We can't answer that kind of question generically about anything that has a big random component, you know. my grandmother smoked, which cigarette killed her? That's an ill-posed question. It doesn't even mean that she died from cigarettes, right? For people who get lung cancer who never smoked. We can talk about probabilities. So what we did was we ran 100 events for each year from 1980 to 2016 that came within 300 kilometers of Houston, downscaled from, to begin with, from 3 climate analyses. These are not climate models, these are just essentially climate data, not quite that. And we ran 100 events each year from 1979 to 2015 for the whole Texas coastline. And for each of these events, we calculated the total rainfall. I forgot to tell you this hurricane model also produces rain. I guess that wouldn't surprise you. At 78 points scattered around Texas. And finally, we ran 100 events each year from 1981 to 2000 and from 2081 to 2100, again passing within 300 kilometers of Houston, from applying this method to 6 different climate models. So here's an example of one storm from the many, many thousands we generated that had sort of Harvey-like characteristics. I think you can see where you are there. Texas is sort of in the upper left, Mexico in the lower left. The storm came in from the southeast around and then went back out. And what that contour is showing you is the total rainfall produced by that event over the course of its life. And that produced more rain. This synthetic event produced more rain than Harvey. That was a really rare event. That produced 1 meter of rain in some places, 3 feet of rain. Okay, but we create thousands and thousands. We were able to say this. This is based upon downscaling 1 climate reanalysis for the whole state of Texas, basically. And it shows, again, on the x-axis, the total amount of rainfall. I'm sorry, that's in millimeters. Okay, you guys can convert. But Harvey's sort of area average total rainfall was about 500 millimeters. There were peaks much higher than that, but the areal average was about 500 millimeters. And by that analysis for Houston, this is for rain in the Houston metro area, that would have been about a 1 in 1,000 year event in the climate of the late 20th century. So for Houston, that, as others have also calculated, a very, very rare rainstorm. Now to get that magnitude in the whole state of Texas, not just Houston, that would be the same kind of chart here with Harvey on it. That level of storm accumulated rainfall would be about a 1 in 100 year event, which means its probability of occurring every year is about 1%. That's its literal meaning. So still a rare event, but somewhere in Texas you would see something like that, maybe on average once in 100 years. Now we're going to look at the climate simulation. So the blue is for the last 20 years of the 20th century, same kind of chart. The shading shows you the scatter among the different climate models we drove our technique with. And the red is for the last 20 years of this century, assuming that we don't do anything to curb emissions. Again, the shading shows the scatter. So Harvey, maybe about a 2,000 year event, according to this, in Metro Houston in the late 20th century, becomes something more like a 100-year event in the late 21st century. So a big increase in probability, not too surprising. That's what we see when we look at the wings of any distribution, is a lot of sensitivity in the tails. So already today, I would argue that the probability of a Harvey-style rainfall in Texas is somewhat larger today in 2017 than it was in 1990, okay? And pretty strong confidence in that. The same thing, kind of analysis we can make for Irma, but this time we're going to look at wind. Again, the same kind of thing. We'll run 100 events a year for 2 periods of time. In this case, storms passing within 300 kilometers of the Caribbean island of Barbuda, and we're going to use 6 climate models to do that. Now we're looking at, again, return period on the vertical axis, but now it's wind speed on the bottom axis. So Irma, if it occurred In the late 20th century, winds of that magnitude in that place would have been an event that occurred every something like 500 years. I've forgotten the exact numbers. But in the future, it will be something that occurs every few decades. But notice that the shading overlaps. That means we have much more uncertainty about that result. The models are much more scattered on that, but the weight of evidence is that we were going to see much more events of that magnitude. Maria, another violent storm of this time, we've done a similar analysis for, and we can see that in the case of Maria, we're looking at winds within 150 kilometers, basically, of a point southeast of San Juan. And that might have been a 100-year or 200-year event at the end of the 20th century. It might happen every 10 years, something like that by the end of this century. So this is why we're worried. And it's not just this technique, and it's not just me. A lot of people who are looking at this reach qualitatively similar conclusions. Now let me try to wrap up the evening by getting down home and specific to North Carolina. I don't need to tell you that North Carolina has had quite a few hurricanes in its illustrious history. So over the modern historical record, North Carolina's experienced over 400 tropical cyclones that passed over or near the state. It ranks fourth among all states in the number of hurricanes that affect it. Collectively, hurricanes have killed more than 1,000 residents of North Carolina and caused more than $11 billion in 2008 dollars in losses. So they're a serious concern for the state. Here are the tracks of all the known historical events, all of them between 1851 and 2013. And they're probably ones we missed, but you can get an idea. They come at us basically from the south or south-southwest. Much more likely to affect coastal regions, obviously, than the interior, but there they are. And I want to briefly review some famous or infamous events. The first one that I'll talk about is an unnamed event from September 1857. We didn't really start naming storms until the 1950s. This is a September storm, and it's famous for having sunk the SS Central America with 424 people aboard and 30,000 pounds of gold. And just a few years ago, the gold was recovered from the shipwreck. You may know that story. It's a fabulous story. It's in pretty deep water, too. This is a hurricane that occurred in 1899. This is the track of the hurricane. The numbers are dates in August or September, with August badly misspelled. The colors are an indication of how strong the winds were at any point along the track. And that remains the longest lived Atlantic hurricane on record, lasting almost actually more than a whole month. It may be, but probably isn't the strongest hurricane to affect North Carolina. But the instruments were destroyed, so we'll never know. And most of Cape Hatteras, all of it actually, was submerged. And all the piers and bridges in coastal North Carolina were destroyed. This is 1899. This is the Outer Banks storm of 1933. That was a pretty serious storm. Hurricane Hazel, which at least according to the records is the strongest hurricane ever to have made landfall in North Carolina, did a terrific amount of damage, 18-foot storm surge, 130 mile an hour winds at landfall. The National Weather Service in Raleigh said all traces of civilization on the immediate waterfront between the state line and Cape Fear were practically annihilated. Every pier within 170 miles of the coastline was demolished again. And remarkably, this storm was still a Category 1 hurricane when it hit Toronto and did a lot of damage up there. So it was a pretty weird storm. Some of you will remember Floyd from 1999. And that took a very interesting track up the coast, produced a lot of rain in North Carolina, some serious flooding problems. More recently, Irene in 2011. You can see the track of that storm. So this is just a sampling of North Carolina hurricanes. What about the future? Well, we've done the same kind of analysis. I did it for this talk for North Carolina. And if we look at the return period of winds of hurricanes crossing the North Carolina coast, we see this. So the blue, again, is for the late 20th century, the red for the late 21st century, and Hurricane Hazel's wind speed is shown by that black line. So a Hazel at the end of the 20th century would have been about a 1 in 100 year event, roughly. And by the end of this century would be something more like a 1 in 30 year event. So a fair increase in probability. Not that much scatter among the different models, so a bit more confidence in that. Here is a random example of one of these synthetic tracks. This is the 100-year storm in the year 2086, 140 knots at landfall in coastal North Carolina. This one is a bad-looking storm because it sort of cruises up just offshore, maintains its strength, and kind of clobbers all coastal cities. Rain is a worse story. So this is Hurricane Floyd's rain is indicated on this chart, about a 100-year event at the end of the 20th century, about a 10 or 8-year event at the end of this century. That's why we're worried, okay? Is this a slam dunk? Nothing we do in science is a slam dunk. But it's the best we can do, and it shows that there's a serious risk, okay? Now we don't have time, I could tell you why I think it will become profitable for us, not just pain in the neck, but profitable for us to deal with that risk by curbing emissions. But I'm happy to talk about that in the questions. So let me wrap it up. In the long term, the observational record of hurricanes is too short and noisy, and the quality is too low to make robust inferences about long-term climate signals. If you think the Atlantic is bad, the rest of the world is way worse in terms of records. Satellite data, which we've had robustly since about 1980, do show a migration of peak intensity toward higher latitudes. And there is some indication that I didn't show you from satellite data of a greater fraction of intense storms. Paleotempestology, the recovery of hurricane proxies from the geological record, is beginning to show some very interesting climate signals. Theory shows that the thermodynamic limit on hurricanes must go up as the globe warms, and it is going up. Physics can be used to model hurricane risk. It's much too important to leave to the statisticians. If there are statisticians in the audience, I apologize. But we have to bring more information into the problem than just bad historical records. The rain of Harvey's magnitude in Texas would have been a 1% annual probability in 1990. It's projected to increase to 18% by the end of this century. And that would suggest that it's already, in 2017, a 6% probability rather than a 1% probability. Irma's peak wind speeds are estimated to have had an annual probability of only 0.13% in 1990, but increasing to a 1.3% in 2090. North Carolina's hurricane flood and wind and flood risks are projected to increase. So this is what I think is the state of the science as best as I know it. I could have presented some work by colleagues that kind of also show similar qualitative results, but we're running a risk. And no, hurricanes are not the worst aspect of climate change by any means. It's going to be global problems of supplies of food and water. But they are serious events that cause serious loss of life and damage. And we should try to do what we can within reason to avoid this risk if we can do so. And I'll leave you with those thoughts. Thank you very much.
Thank you very much, Kerry, for a wonderful talk. I asked Kerry at the beginning whether he would be interested in answering questions, and he said, well, that could be the best part of the whole evening. Yeah. So I would like to invite questions.
Hurricanes transport a lot of heat poleward. And I'm wondering with future intensification, etc., what might be the possible feedbacks on other heat transport mechanisms? Be it mid-latitude cyclones or even, the Atlantic meridional overturning circulation, for instance.
That's a
Any
really,
thoughts on that,
yeah.
or is it just peanuts?
No, it isn't. But it's not the poleward heat transfer it turns out it's not that's important. It's the vertical transfer. You're basically taking heat out of the ocean and putting it in the atmosphere, except you're not. I mean, that's the short-term effect. In the long term, you've upwelled, stirred up to the surface a lot of cold water, which has all kinds of interesting effects. And that water gets reheated by the sun, and that basically represents a drawdown of heat from the atmosphere back into the ocean. Turns out there's about 10 times more heat that gets drawn back into the ocean after a hurricane than went up in the hurricane. So you're pumping heat into the ocean. And the ocean has to do something with that, and it redistributes the heat both in latitude and longitude. And we're only beginning to understand the climate impacts of it, but it turns out to be a big number. So it's a really good question. We think hurricanes do have a feedback on the climate system, but we're only beginning to understand what that is.
I'm Manzili Kokai, an NCCU student. When you said that the trends were going from, I think it was the hurricane trends were going from the middle towards the poles, I was wondering if there was a chemical or like physics reasoning behind that, or what's the reasoning behind that trend shift?
Okay, that's good. So the latitude at which hurricanes reach their peak intensity has been drifting poleward in both hemispheres. And it's interesting that when you put carbon dioxide in the atmosphere, you get more bang for the buck thermodynamically, if you will, in the subtropics than you get in the deep tropics. So the thermodynamic potential is going up a little bit in the deep tropics, but it's going up a lot in the subtropics. And that's why we think hurricanes are reaching greater magnitudes in the subtropics now than they used to. So it does sort of jibe with what we expected theoretically.
Of course, we're familiar with cyclones in the Western Pacific, but on your global map of potential intensity, it looked like there was a hot spot in the Arabian Sea.
Yes.
Are there really cyclones there?
So that's a great question. The Arabian Sea does have cyclones, but not nearly as much as the Bay of Bengal. And the reason it turns out to be that when the monsoon really gets going, there's a lot of upwelling of cold water off the Arabian coast. You did mean the Arabian Sea, right? Not the Red Sea or the, right? So that tends to suppress hurricanes, but there are. And one of the projects I'm engaged in with a colleague at Columbia is to try to assess the long-term risk of tropical cyclones in Mumbai. Because Mumbai hasn't had a really bad one in a long time. And the only one we could find from the 19th century, which purportedly killed hundreds of thousands of people, turned out never to have existed in the first place. It's one of those things that there was one newspaper report that turned out to be totally wrong, that got amplified over the media. I'm embarrassed to say it's in the back of my Divine Wind book as a record storm. Never existed. Historians do their job. There have been, on the other hand, some really bad storms, in particularly the eastern part of the Arabian Sea.
So you mentioned about the profitability of predicting these storms in the future, and so I was thinking about the research that like insurance companies are going to be doing on like how risks are going to be changing in the future. And I was wondering what happens to the research that like insurance, like actuarial companies are doing. Is there like collaboration between them and academia, or do they just like hold on to all of that for their own purposes? Like how does that work?
Well, that turns out to be a very interesting question, because that scene that you just described is right at the moment evolving rapidly. So up until this year, your question turns out to be extremely timely, it was done by the big risk modeling companies mostly. Risk Management Solutions is a big global company, AIR worldwide, 2 or 3 companies. And it was all proprietary. It was all in-house research. They produced black box models that the companies used to set your insurance rate. And nobody knew what was in them except the in-house people who ran them. So When I started to develop academic risk modeling, others soon followed, and there's a group at Columbia that does that. So just a month ago, about a month ago, we had a big meeting at Columbia that brought the risk modelers and the academics together. And so we're going to open up this enterprise and make it into an interesting intellectual endeavor and open up the risks so that everybody can see what they're getting, in the case of the companies, for their money. So this is a very rapidly evolving landscape, and I think that if it weren't for academic stovepiping, which is a serious problem, that I would say there's a big future for academic research that brings science, especially physics, to bear on assessing societal risk. It is just starting to happen, and I think it's very exciting.
How are things coming together with paleo reconstructions of the past? Are you able to learn better about things like intensity in addition to just the occurrence? And how far back can you go now? And how far back do you think we'll be able to go in the near future?
Well, that's another excellent question. Right at the moment, we're not really able to say much about intensity. The records show, basically reveal storms greater than some threshold intensity, but greater than that, we don't know. With one exception, there was a study done in Florida by a colleague of mine that looked at sand washing into sinkholes. You know all those sinkholes in Florida? There seems to be a new one every day. They could detect how far inland storm surges went from looking at a succession of these sinkholes. So in a few places, it at least tells you the magnitude of the surge. And there's some whoppers in Florida's history that people who live in that part of Appalachian Bay probably don't know about. There are other techniques I didn't tell you about. That hurricane rain has a chemical signature. It's an isotopic signature. It's light in the heavier isotope of O18 of water. And that gets recorded in certain places, like in caves. And we might be able to use that to go back a long, long time. And that's not just coastal. That's inland as well. So I have a lot of hopes. Right now, 6,000 years is the longest record we have.
Okay, well, I'm sorry we don't have time for more questions, but I am conscious of the fact that the evening is getting late. So I would like to conclude by thanking Kerry Emanuel very much for the lecture you just gave us.
Thank you.